All right. So we are going to look at some applications of this and try and calculate the constraint force in some simple situations and solve the equations without actually switching to generalized coordinates where the constraint disappears. But before that, are there any questions about derivation or anything about the first session?
Just to clarify in my mind about the like altering the lambda j's so that the QIs are independent.
No. Okay, I'm very glad you asked. We are not altering QJs, lambda j's to make QIs independent. The first thing you do for this one is that you pick up a set of Qs that they are independent. Okay, so if we let's start the full Cartesian coordinates, we'll start with 3 and r's, x's, y's, and z's, and we will pick up 3 and minus k of them that are independent. We can always do this, right? So we will have k kinematic relations, k constraint equations, and we're going to choose among our Cartesian coordinates 3 and minus k of them. Okay. Now we look at the remaining ones. So the remaining ones are also in the sum at this point. Okay. But we set our lambdas in such a way that the coefficient of the remaining ones are 0. How many are there remaining? K of them. How many lambdas do I have? K of them. So I can always do this. It can always be done. Now, once I do that, because their coefficient is 0, they drop out of the sum. So I have a reduced sum. This time now, not going from 1 to 3n, but going from like 1 to 3n minus k. Now all the displacement there, all the virtual displacements there are independent by my choice. This is how I started everything. Okay. And then their coefficients must also be 0 because they're independent.
Can we think of it like it's going to still be Cartesian coordinates, but like in standard Cartesian coordinates, we have x and y. But for example, if we consider the pendulum and we choose our coordinate system as the polar coordinate system, then I'm assuming one of the coordinates will drop out.
But it depends. So if you want to utilize the constraint equation, so your constraint equation is something like going to be r minus a, where a is the length of the distance of the bob from the pivot point, is equal to 0. Right? So you're going to have something like this. So g of r, let's put in theta as well, r minus a is equal to 0. Right? This is a constant. This is the length. So if you want to use this and solve, recast your equations this way, then your constraint equation becomes just 0 equals 0. Okay? So if you want to, when you use this, everywhere you see r, you just substitute a. If you do that in the constraint equation, you just get 0. So this is not a constraint equation. It's not useful. If you don't do this, if you keep your r, if you don't substitute a wherever you see r, then you're going to still have 2 coordinates, and you're going to get one constraint equation.
So I'm just trying to figure out the independency. So when I choose x and y, they're not independent.
That's right.
I'm assuming, because there is a connection between x and y in terms of cosines and sines. But when I choose r and theta, I make the coordinate system independent. Am I correct?
So that is for the pendulum problem, yes.
It's a very basic analogy. I know it's a very basic question and maybe more complicated in other questions. But so x and y in this case are not independent. But when we choose the polar coordinates for the pendulum case, we have the independent coordinate system so that we can say that what is in between the parentheses is equal to 0.
Right. So the reason why this distinction occurs is because your constraint you write in polar coordinates does not involve one of the coordinates. right? So they're in fact independent. But if you write this in x and y, then it's going to look something like this: x squared plus y squared minus l squared is 0. Okay? Now it involves both of them, so they are not independent unless you utilize this. But you can always choose one, and it's going to be independent, not only because it's a it's just one, it has to be independent of everything. But if there are like other sets here, other stuff, I don't know, this pendulum is like a double pendulum, something like that, then this equation tells you that you can choose just one of these, and the other one is going to become independent. You can, by independent, what I mean is you can give it any value you want without altering the others. Okay? So because in polar coordinates, the constraint looks like this always happens. Right? So you theta, I mean, without even considering this, theta is going to be independent of r. Okay? But like with this constraint, it doesn't allow you to pick theta or r. Like this one allows you to choose your independent coordinate to be x or y. This one doesn't. Okay, you are forced to choose theta as your independent coordinate.
Yes.
But regardless of the form of the equations, how many they depend on, if the constraints are not contradictory with each other, like if they have a solution, then you can always pick k of them, k of your coordinates, Cartesian coordinates or whatever, k of your initial coordinates, and the remaining are going to be independent. Because you can always, in principle, recast your constraint equation such that those k are given in terms of the remaining ones. Right? This is what solving these equations correspond to. Now, they could be nonlinear, they could not have solutions, but okay, then your constraint is not physical. What can I do? Right? I mean, that we can't solve an unphysical problem is not a problem for us. Right? That's okay. We don't expect it. But if they are physical, then you should be able to express k of your coordinates in terms of the other ones, the 3n minus k ones. And we don't need to choose those. That just in principle, I can do this is enough. Because eventually they come to the same footing. Right? So the coefficients of the ones that I can express with the constraint equations, they are 0 by choosing these guys. The coefficients of the rest is also 0 because they're independent. Right? I never actually go through the trouble of picking those up. That I can pick those up in principle is enough for me. And this can probably be proven, but for a physical problem, that you should be able to explicitly write those. Not explicit, but that there should be some solution to k of the coordinates in terms of the remaining ones. It should always happen.
Okay, thank you.
Any other questions? Okay. Now again, for those issues, I think Hamilton's principle is not very transparent. Now going back to the Virchow-Work equation is a little bit easier for me, but this is very subjective. Perhaps this is the same as the other one. I guess it all depends on how you learn these things the first time, and yeah, just sticks. Okay. Now we're going to look at a problem given in the book that's very similar to the pendulum actually, and it's a classic problem where you have a half sphere. Okay. So something like this. And so this is the center. This sphere has radius a, and I'm going to have a coordinate system that's kind of dictated on us. So this is x, y, and z, and we have a particle that starts at the top. And let's use another color perhaps. And slides down the sphere. Okay? And initially, such that it remains in it starts in the xz plane. Okay? Starts at the top and in xz plane. And this is a question that you probably have seen a freshman class. It's really classic, either homework or exam or something like that, example problem. And the question usually is, when does this leave contact? So how do you solve this with freshman methods? What's the criterion for losing contact? We're going to write down some Lagrangian and do it this way now, but do you recall how you do this with the freshman methods?
I think it was about the R minus A being larger or equal to 0.
I don't know. That might work. I don't see how. But so who is here? Again, are you here?
Buradayım hocam.
Did you solve this problem before?
Yok,
Did you
hayır.
see this problem?
Yok hocam.
Okay, how would you do this with freshman methods though? So you're sliding down, and at some point you're going to lose contact. If this is a real sphere, it really does happen. I never did this myself, but so what will be the criterion? Not using the methods here, but from the freshman year. What happens when you lose contact?
The normal force disappears.
The normal force disappears. Right. So that normal force is what's preventing us from getting into the surface. It's in fact a constraint force. Right. So we actually did this. But so how does normal force disappear? Well, as you move down, you're going to gain some speed because of conservation of energy. It's the simplest way. Otherwise, it's not a linear equation. But you're going to gain some speed, and that speed is going to lead to this circular motion. Okay? That circular motion is supported by two things, and one of them is normal force. And if you don't need normal force anymore, then you lose contact. Okay? So that's the idea. You set up the equations, you write an expression for centripetal acceleration, and that expression is going to involve normal force. And if you set normal force to 0, you find some answer. Okay? This is in Ohanian, for example, Ohanian Physics 2nd edition, which is what I used for undergraduate freshman course. Definitely has this. I definitely remember solving this problem. But how do we do this over here? So they're asking us to switch to some generalized coordinates here, actually. And one of them is going to be this angle theta. Okay. And the other one is going to be just this r, our distance from the center. And our constraint equation is what we had for the pendulum before, that r is equal to a. And the way they handle this in the book is a little bit confusing. They go back and forth between substituting and not substituting a. I think we can do this a bit more cleanly. I try to at home to do this a bit more cleanly. So first of all, it starts in the XZ plane. And so we can ignore the y coordinates. So it's this statement given in the book. How do we justify this? Can we really ignore the y coordinate? So that if you start in the XZ plane, the motion stays in the XZ plane. Why is this? Or how would you justify this?
If there are no external forces, net external forces, in the y direction, let's say, the particle will keep its motion in the xz plane.
But why? I mean, you don't know the force yet. You don't know the force exerted by the sphere yet. So how could you come to that conclusion? Yeah, there are no external forces, but the sphere is perfectly capable of exerting the force in the y direction, except when the motion starts this way. So how would you justify it?
We can just choose the x-axis as the motion axis.
Yes, that's what I did, because that's what they told me. It starts in the XZ plane.
the normal force will be, from the outwards, r direction. So
Okay. So the only force that's acting on the sphere is the normal force, and
Yeah.
that in that plane has no component in the y direction. So
Yeah.
combining the argument of you two gave, I'm satisfied. Right? There's a more formal way to put this, but this is good enough. Okay? So it does state that. So I'm going to ignore the y coordinate. Now I'm going to write the Lagrangian. Right? So first let's write the kinetic energy. This is going to be a half x dot square plus z dot square, okay? And potential energy is going to be mgc. Now, as the book suggests, it's a good idea to switch to polar coordinates here, and there's again a typo in the book. I think it's so unclear that I'm not really sure what they're doing, but I'm going to switch to polar coordinates, and if you look at this from the side, it looks like this. So maybe like that. Z and X. So this is R, this is theta, but X is going to be R. So this is the opposite one, sine theta. Z is going to be R cosine theta. Okay. And I can, of course, invert these, but I don't need to. So I need to take this and rewrite this in that form. So x dot square is going to be r dot square. Let's write this slowly.
Hocam, excuse me, why did we neglect the mass term in kinetic energy?
Oh, I forgot it. I didn't click it. Thank you. So x dot is going to be r dot sine theta plus r theta dot cosine theta, and y dot is going to be r dot cosine theta minus r theta dot sine theta. So I'm going to calculate x dot square plus z dot square. So this is going to introduce an r dot square sine square theta, r dot square cosine square theta. I add those up, I get r dot square. I'm going to have r dot sine theta, r theta cosine theta, and then r dot cosine theta with a minus sign. So the cross terms are going to cancel. I'm also going to have the same term over here with the sine square plus cosine square theta adding up. So this is going to be r square theta dot square. Okay. So the cross terms disappear, and the off terms just add up because sine square plus cosine square is 1. Okay, so there's a simplification, and this one is just going to be mg r cosine theta. Now, my Lagrangian then is going to be a half m r dot square plus r square theta dot square plus mg r cosine theta. Now to this, I'm going to add the constraint equation multiplied by some lambda, and I'm going to take the variation of this. Yeah. So plus lambda r minus a plus lambda r minus a. And let's do this. Let's not clutter this. I'm going to erase this. I don't think we need visualization much. This we already used. This we can keep in mind. This perhaps we keep. You want to go back? I don't know. So the relation with respect to r is mr theta dot square plus mg cosine theta. Okay. The variation with respect to r dot is going to be r dot, and lambda times the variation of the constraint with respect to r is just 1. So this gives me an equation. All of this gives me an equation. What's this? R double dot. Okay, so I take the, let's be consistent. I take the derivative of this, subtract this one off, minus r theta dot square minus mg cosine theta, and then I subtract this one off, plus lambda 0. So this is the first equation. The second equation, you just go through the same thing. For theta, we get r squared theta double dot plus 2mr r dot theta dot plus mgr sine theta equals 0. Constraint equation doesn't depend on theta, so Lagrange multiplier doesn't enter this one. And we also have r equals a. So the book is taking some shortcuts. They're not writing down these this way. They actually show you the equations after you substitute this into these ones, right? This substitution, of course, the time derivatives of r disappear. You get some simplified equations. And when you solve one of these two and substitute into the other, so this one you eliminate by putting r equals a, by putting a wherever you see r, and getting rid of the time derivatives, then this simplified equation can be solved and substituted into this one. And the solution is actually given in the book. I'm not going to go through this, but it is a useful exercise to go through this on your own. So what is the results? Oh, I think I left that one, so I'll just copy from the book. I was thinking this would be too simple and started solving on a small piece of paper, but it just got complicated. So you get theta dot square is minus 2g by a cosine theta plus 2g over a, and perhaps more importantly, lambda equal to mg 3 cosine theta minus 2. Now, if you recall what we did at the beginning of the lecture, this gives you, when lambda is 0, the constraint force is also going to be 0. So the constraint force here is the normal force. So you want to figure out when you lose contact, when this is equal to 0, contact when lambda is equal to 0, because that gives the normal force. So to write this again, just to remind you what we had gotten for the constraint force, J is gradient of I, which is J equal to 0. So to get this 0, you need to get this 0, and that happens when lambda is equal to 0. And that corresponds to some funny angle. The cosine theta should be 2/3. and result that you can also get by using Newtonian mechanics methods. Are you confident you can get this with Newtonian mechanics methods? If I ask this in an exam, it's a level 3 question, Ohanian. Those are usually not very easy. But at this point, there aren't that many questions that I can ask. Just something to keep in mind. Sometimes the threat is stronger than the execution. Do you know who said that? The threat is stronger than the execution. Does any of you play chess? Like enthusiastic level? It's one of the old classic masters, Steinitz or Zukertort or something like that. All right, maybe Ninjovic. Now let's look at another problem, the Atwood machine. And let's try to get that one. So these are really simple, but we don't want to get too complicated. And that one, actually, we can solve in full. And that you definitely can solve with freshman methods. Right? So, machine. So I have a pulley here, and I have two masses connected by some rope. And the idea is, of course, to find the acceleration of these masses. And in this case, we are also going to use the Lagrange equation of the first kind to find the tension in the force. Yeah. So again, we have to choose some coordinates that we can write out Lagrangian in a nice way. So one way to do this is to choose a coordinate system that looks like this. So let me use a different color. Z. And then these guys are going to get coordinates Z1 and Z2. And we can write kinetic energy trivially. I have M1 Z1 dot square plus a half M2 Z2 dot square. Agree? There's nothing here, I think. The potential energy is M1 Z1 or 1 G Z1 plus M2 G Z2. Or is it negative of this?
It shall be minus, I guess.
Is it minus?
Okay.
Can you convince me it's minus?
It's below the z coordinate. Like
below the
minus
z
z.
coordinate? So is there such a rule? If it's below the z coordinate, it has to be minus z? How do you reason?
So far we have done it this way, and
Well,
Okay. That's the way things are since time of Newton. That's
so
Yeah.
can we say it depends on the choice of reference frame? If we select our
It
Z1
does.
and Z2 from the pulley, then we also should define a potential according to the same level.
yes. So we are defining. So the where you choose the zero defines only where the zero level of potential energy is. So when these guys are at the pulley level, there is no potential energy corresponding to them. But this choice just dictates that. The other one is more critical. I chose up as positive. The z-axis is going up. So it is below z-axis, but if I flip this, presumably I should introduce a negative sign there. So how do I decide? What's the physics? This is not something you can just relay back to Newton because you don't know what Newton will choose here. I just chose this to be up. And you could say that, okay, in our freshman classes, we always choose Z to be up, and we always introduce a negative sign over here, but that's not good enough for me.
So
I want a justification.
potential itself, I mean, I'm not going to say it's not physical, but what we consider in the motion, motion of a particle is the change of potential. So whatever we choose, or either positive or negative, as long as we keep the signs accurate
Or consistent, let's say.
consistent, yes, exactly, consistent, then we will arrive at the same equation of motion.
No,
No?
the force is going to be reversed. If the potential energy picks up a negative sign, force is the negative gradient of potential energy. The force is going to be reversed. So you're not going to get the correct equation of motion. So if you were just calculating acceleration, this won't be a problem. But now you want to calculate tension as well. So you have to be careful. If you're subtracting off or adding the effect of gravity with respect to tension, it's going to make a difference. It's going to, well, I mean, you can notice what the mistake you made and fix it. But there's so you are starting in a way that I really liked. So it is the difference in the potential energy that's important. So how does the potential energy change? Let's think about that. So potential energy is a convenience function. It's not something you really need. It's convenient that for a conservative force, the work done does not depend on the path, but only on the 2 points. So we can define a state function just based on the points. And the difference always remains the same, regardless of how we go from one point to the other. Right? So one way to think about this, how you get, whether this is negative or positive, is what does happen when I go down? Now, when this, let's say that this is just a free mass. It's moving down in the gravitational field. What does it do? It gains kinetic energy. So its potential energy must be decreasing. Right? There's no other way around this. As you go down, the potential energy is decreasing. This is independent of the coordinate system you choose, blah, blah, blah. The expression you write over here has to be consistent with that. As you go down, the potential energy is going to decrease. Now, as I go down, this is C1, is it going to increase or decrease?
Depends on, it depends on the
choice.
masses.
No, it doesn't depend on the masses. As I go down, as this mass goes down, is the C1, its coordinate, is it going to increase or decrease?
So if M1 is going down, Z1 will
fine.
increase.
Let me ask somebody else. So, who's here? Ayşenur Çelik. Ayşenur, are you here? Okay, maybe not. How about Seçkin Berkay?
Yes, hocam.
So, do you remember the question?
Z is going down. Is it decreasing or increasing?
Yeah, is this Z1 going to decrease or increase? The potential energy has to decrease because kinetic energy increasing. So, do I keep it that way or do I introduce a negative sign? Does Z1, as I go down, decrease or increase?
It's like line coordinate system, and we are going to the minus.
This is a yes
way.
or no question. This is like either or.
It's decreasing.
It's decreasing. Can you convince me? Okay, now bring the elaboration.
It's like a line coordinate system. We are going towards the negative sign, negative side,
To negative
as we
infinity?
go.
Okay, so it's getting more
Kinda.
and more negative, right? So
Yeah.
it's starting with some small negative number. As I go down, this gets a larger negative number. Yes?
Yeah, exactly.
Yeah, so it is decreasing. As I go
Yes.
from -3 to -5 to -15, this number is decreasing.
Yes, hocam.
If I just call this the potential energy, as I go down, this is going to decrease. As this mass goes down, that is going to decrease. I don't need a negative sign. Yeah. So I don't know what you were doing previously, but perhaps you were choosing it this way. Now, if I did that, it will be a different story. I picked up the coordinate system myself. I picked this one. As I go down, now z is increasing. Z1 is increasing. It's becoming more and more positive. Then I need the negative sign over there. Okay. So that depends on your choice of coordinate. This is not surprising. Of course, if you flip the coordinate system, all the components corresponding to that axis is going to pick up a negative sign. There's no magic here. This is something you must have done before. But you have to think. And the way to think about this, so the one way is what Shaheen was saying. It's a bit long, but it will work for sure, because it's very formal, that you calculate the work done, and you remember the definition of potential energy is that delta U is the minus work done, which is F dot PL, the line integral from both places. And that line integral, of course, simplifies very rapidly for this situation. But the other way, which is the way I prefer, is to say, what does happen if I go down? Does the potential energy increase or decrease? It has to decrease. Why? Because the kinetic energy is increasing. Their sum has to remain the same. Okay. All right, but I claim that this is correct. And then the Lagrangian is T minus, well, we call this U, didn't we? So L is T minus U. So then I'm going to pick up a negative sign. There, minus one G, one minus G, C2. Okay, that negative sign is coming from here. Okay. Now we also have to introduce a constraint. Okay. And the constraint is so as this one goes up, as it increases, this one decreases. As this one increases, this one decreases. What does that suggest? When something is increasing, the other one is decreasing. That their sum is equal to some number, right? So I'm just going to say my constraint is Z1 plus Z2 minus L is 0 for some L. Okay, so let's check what I did at home. Okay, I can't figure it out. But let's write down our equation. So this one is going to be minus M1 G del L by del C1 dot is going to be M1 C1 dot. So del L, sorry, del G by del C1 is going to be 1. So let me try to write the Lagrange equation second like the way we wrote it before. D by dt of del L by del Qi dot minus del L by Qi. So flip the plus or minus here, plus sum over the constraints, lambda J, del G, J by del Qi is 0. Okay. So I take the time derivative of this, M1, Z1 double dot, minus plus, M1 G. So the variation is just plus lambda is 0. And then we have something similar for plus M2G plus lambda equals 0. Again, if I'm making mistakes, please try to catch them and stop me. And then I have the constraint equation, which is Z1 plus Z2 minus L is 0. Now, how can I utilize this? Well, if I take the derivative of this twice, then I get Z1 double dot is minus Z2 double dot. Yes, yes, okay. And so if I subtract these side by side, I get N1 Z1 double dot minus N2 minus Z1 double dot is plus N1 Z1 double dot. This is N1 minus N2G. And this one just disappears. 0. So Z1 double dot is then, I move this to the other side. M2 minus M1 by M1, this is M2 plus M2 times G. Which is what we already know. The acceleration, at least the magnitude, should look like this: the difference of the masses divided by the sum of the masses times G. The driving force comes from the imbalance, which is the difference of the masses times G. And there's a common acceleration, so you divide by the total mass. So this is the correct expression for the acceleration. Okay, now we can take this and substitute this into over here, and we can solve for lambda. Is there a simpler way? Yeah. We can just add these up. Then these are just going to cancel. So let's do that. So M1 plus M2. Oh, they're not going to cancel. No. Which one is simpler? Well, let's add these up. Yeah.
If we substitute Z1 double dot into the first equation,
Yeah.
then we will get M1G twice because that Z1 double dot also has G. So we will have 2 times M1G, and in parentheses there will be cancellations.
Yeah, okay, let's try that one. That was my first instinct, and I thought these would cancel, but they don't because they have different coefficients. So let's try substitution there. So M1 times M2 minus M1 over M1 plus M2G plus M1G is minus lambda. Let's keep it this way. So this one becomes M1, M2 minus M1 square plus M1 square plus M1, M2 over M1 plus M2 G is equal to minus lambda. These guys go away, and we get 2 M1, M2 divided by M1 plus M2. Or minus lambda is 2 M1, M2 divided by M1 plus M2 G. Okay, how does this relate to the force? What's the relationship? There was something trivial which I did not write. How does this translate to force? So look at this equation. So we already wrote an expression that looks like this: d by dt del L by del Qi dot minus del L by del Qi is minus sum over j's onto j del j over Qi. You already seen an expression like this.
So
Or this is equal to what?
generalized force.
It's the generalized force. Very good. Okay, so this is how you get from your lambda your generalized force. In this case, there's just one constraint, and there's just one expression. So this is just going to be, so the derivative of its constant with respect to coordinates is just 1. So this term is just 1. And this is in fact your tension force. This is your constraint force. Now, one possible thing you can try here is that what if you have chosen your sign of the potential energy incorrectly? I claim that if you do the algebra correctly, this is going to be okay, because you're just interested in the magnitude, right? When you see this, you say, okay, this is the magnitude of the acceleration. The heavier mass goes down, the lighter mass goes up, if you start from this. But this one, it can turn out completely wrong, because whether you're adding the tension force to the mass going up or subtracting tension force from gravity for the mass going up or down is going to make a difference. I'm not sure, but I think this is going to get the wrong answer. And by the way, this one, so this is minus lambda, and I'm just saying this is the force and so on and so forth. First of all, you can never get the magnitude, the direction of the force using these constraint equations. The way you set them up, okay, I've chosen this plus arbitrarily. Remember how I introduced the Lagrange multipliers? I said, okay, this is 0. I can add this or subtract this. And I chose to add it. Right? But it is 0. I could as well subtract it, and this would have the negative sign. So that is ambiguous by our construction. There's no problem there. You have to look at the physics. And in this case, it is actually a little bit weird. Right? So for this generalized coordinate, it's up. For this one, it's down, and so on, because the tension force direction is ambiguous. For this one, it is going this way. For this one, it's going this way. So they're in the opposite direction. So in this one, there is no problem. But in general, if you really need the direction, you need physics. This will never tell you the direction of the force. It will only tell you the magnitude. It cannot. It's how we constructed this thing. How we would get that? Well, I really don't know. Well, I know there's a way, but I don't know the way. Okay, let's put it that way.